Let me take a couple of minutes to read the notation here of these partial derivatives. These are called partial derivatives, and that's because you're going to treat one variable or another as a number. So you're partially taking the derivative of a function that has both an x and a y in it. This first notation means the partial derivative of a function f containing x and y variables with respect to x, which means we're going to treat y as a number. This next one means the partial derivative of a function f in variables x and y with respect to y, which means we're going to treat x as a variable, as a number. So the subscript tells you which one is the variable, okay? Now, each of these four that follow here are second derivatives. So you're going to take the derivative of the derivative. And when you have the subscript xx, that means take it with respect to x the first time and with respect to x the second time. And both times treat y, if there are any y's left, as a number. And then f sub xy means the second order partial derivative with respect to y both times. So here we're going to treat x as a number. And these two are really interesting because when you take it with respect to x the first time and y the second time, or y the first time and x the second time, these are going to always come out the same. So it doesn't matter which order you do it in. So if you get 10 for the first one, you'll get 10 for it in the other order. So in the first one, the first time, y is a number. And the second time, x is a number. And then, so in other words, we're going to go up here to this f of xy with respect to x, okay, find the partial derivative of function f in variables x and y with respect to x the first time, so y is a number, but the second time it's with respect to y, so that means that x is a number. So this time, this fyx is going to be the first time you're going to have x as a number, and the second time y is a number. So that sort of describes what this notation is. And so in this video that follows, I'm going to stumble over saying fx, xy. I mean, it's pretty complicated, right? It's just so many variables. It's kind of lazy, but you can just write f sub x, f sub y, f sub xx, f sub xy. But you have to remember that in these problems, we're finding critical points x and y. We're not finding you know how we would find a critical number and put it on a number line? Well, this time we're finding critical points, and you'll see that further described in this video. Find all points where the given function has any local extrema and identify any saddle points. So this is a multivariable function, so the traditional first derivative test doesn't work. There's a test, and we'll get to the test in a few minutes, but there's a test that we have to do to decide if we have a local maximum. So some sort of a 3D shape maybe that has a hump like this would be a local maximum. And then it might have a hump down here like this, local minimum. Remember, this is 3D. Or it could be a shape that's similar to this, which is 3D, and that point right there is called a saddle point because this kind of looks like a western saddle there. All right, so the first thing we do is we find the derivative of f with respect to x, okay? So that means y is a number. So that's going to give me a 16x plus a 0 minus 24y, because remember this y becomes part of the coefficient, so there's 24y, and then plus 0 again. So we have 16x minus 24y. So that's our first derivative of f with respect to x, treating y like a number. Then we find f of y, xy. So this time, with respect to y, treating x like a number, we will get a 0 for the 8x squared. And then that's going to be 9y squared. 3 times 3, 9. Reduce the power by 1. Still your regular derivative rules. This time it's going to be minus 24x, because that's the coefficient of y, because x is a number, plus 0. So we get 9y squared minus 24x. Now, instead of getting a critical number, we're going to get critical points. So critical points will have both an x and a y, and we get those by taking fx xy equal to 0 and fy xy and set it equal to 0. So I've got 16x minus 24y equals 0, and I have 9y squared minus 24x equals 0. Now, I can't use the elimination process here because I'd still have an x and a y. So what we want to do is let's go ahead and solve this first one for y. So let's see, let me solve it for x. So I've got 16x is 24y. Divide both sides by 16. Divide both sides by 16. So x becomes, reduce that fraction, 3 over 2y. And so now I can use what's called substitution. So instead of the x, I have 9y squared minus 24 times 3 over 2y equals 0. So you'll notice now that my equation has only y variables in it, and so I can actually solve it for y. Now, don't be alarmed that there's a fraction here, because look, this fraction is going to reduce out nicely, because 2 will go into 24, 12. 12 times 3 is 36. So this equation is now going to reduce down to 9y squared minus 12 times 3, 36y equals 0. All I have to do is factor out the common factor, 9y, y minus 4. So the first factor, 9y, can be 0, or the second factor, y minus 4, can be 0. So divide both sides by 9, y is 0, or y is 4. Now, those are not critical numbers. Those are half of your critical points. You don't have your x's, you just have your y's. So I'm going to go back to 16x minus 24y equals 0, and I'm going to find my x's. So if y is 0, 16x minus 24 times 0 has to come out to 0. 16x minus 0 equals 0. 16x equals 0, divided by 16. X is 0. So that completes my point. My first point is 0, 0. Okay. My second point, y is 4. So 16x minus 24 times 4 equals 0. Is 16x minus 96 equals 0. 16x equals 96 divided by 16, and x is 6. So that completes my second ordered pair, 6, 4. So those are my critical points. Critical points, not critical numbers. You have to have an x and a y. All right, now, we're trying to decide, is this a local max, local min, or a saddle point, or do we not have enough information? So let's look at what the test is for determining. So I'm going to go back over here. We've got to find this thing called D, but before we can find D, we have to find fxx of xy. So that means take the derivative of f of x, f sub x, right? So you've already taken the derivative with respect to x once, take it again with respect to x. Then again with respect to y. And then opposite, first time x, second time y, or first time y, second time x. So let's look at these derivatives. I've got fx xy is 16 minus 24y. So that means f xx xy. So that is a second derivative. You take it of f sub x, right? So you take the derivative of the first derivative, and we get 16. Because with respect to x, the y is going to be a constant. Now we're going to do fyy of xy, of f of xy. And so with respect to y, that's going to be 18y, right? Now, the last thing we have to do is fxy. And so fxy is going to be, well, see what happens here and why it doesn't matter? Look, it's going to be negative 24y. And if we take it with respect to x of f sub y, look, it's negative 24x, so they're both negative 24. So these are the three things we need. F xx of xy. So, let me say that properly. It's the second derivative with respect to x, taking the first derivative with respect to x of a function, f, at a point xy. So it's kind of hard to say, which is why I always flub it up. All right, we need to know this f xy. Notice I left off my ordered pair xy. It's a little lazy, but it's okay. And then we need this. So we have, go to another page here, f xx xy is 16. F yy of xy is 18y. And f xy xy or fyx xy, both of those came out to be negative 24. So our D value is fxx, I'm going to take the shortcut, fyy multiplied together, subtract fxy squared, right? So I'm just going to fill that in. So it's going to be 16 times, oh, and by the way, the first time we're testing is the 0.00, times, so look, fyy is 18y, so it's 18 times 0, okay, minus negative 24 squared. Now, all of this is going to turn out to be 0, because look, if you do fyy at 0, 0, that's going to be 18 times 0, so that gave me a 0. And here's where a lot of the mistakes come in. This is going to be a negative 24 times 24. So it's negative 24 times, it's the opposite of negative 24 squared. So it's negative 24 times negative 24, which is 576. But it's the opposite of that, so it's minus 576. You have to think of it this way. This is a negative and a negative 24 and another negative 24. So look, you have 1, 2, 3 negatives, therefore it's negative. So when D is less than 0 and fxx is greater than 0, you have a minimum. So this is a local minimum at 0, 0. Now they don't ask us to actually go in and evaluate it. Okay, you know, like go in and put 0, 0 into the function and find the actual value of the local min. They don't ask for that. They could, and we would just substitute it back into the original function. Now we got to test the other point, because remember the other point, let's see, what was our other point? 6, 4. So we've got to test 6, 4. So testing 6, 4 this time. So fxx is still 16. Fyy at 6, 4 is going to be 18 times 4. Well, 18 times 4 is 72. So that's 16 times 72, all right, minus still negative 24 squared, all right? So 16 times 72 is 1152 minus 576, okay? And this time, 1152 minus 576 is actually positive 576. So we have a D that is greater than 0 and fxx that is also greater than 0. So this is a local minimum at the point 0.64. And those are our final answers. So the main thing to remember is that when you are taking the derivative, when you have multiple variables, it's not implicit differentiation where you have to write the dy dx. This is, you just treat, in this case, you just treat that variable, that other variable, as a constant, as a number, right? So like we did when we were taking these derivatives, and we said, oh, okay, so y is going to be a number, and therefore its derivative is 0. Okay, so just remember to treat that other variable as a number, and that when you have the notation with the double x or the double y, that means you take the derivative a second time, paying attention to which one of the first derivatives you have to use.